Good morning and welcome to today's lecture. It's been a long series and it's been a long semester, but I believe the grace of God is still responsible for our life. In the previous lecture, we looked at a multi-step predictor method, specifically the Adams-Basford method. The Adams-Basford method. But here, these are corrector method. We usually predict with some corrector schemes, either single step or multi-steps. Then we correct the solution with, or we fine-tune the solution with some of these methods. These are implicit schemes. So explicit schemes are predictor methods and implicit schemes are corrector method. I've been repeating this over and over so that you get it. It doesn't become so confusing. So there is a general formula for the Adams-Moulton method. That's a general formula for the Adams-Moulton's method. And as it was in the case of the Adams-Basford method, wherever you are truncating what is in the bracket, where you truncate will give you a different order. So when I truncate here, I have first order. When I truncate here, I have second order. When I truncate here, that's from here to all this part, that's the third order Adams-Moulton method or AM3 method. When I truncate here, I have the fourth order Adams-Moulton's method, and these are changed in F. The other one was changing Fi. This is just changing Fi plus 1, which is Fi plus 1 minus Fi. And you can have the second change, and it is easy to do that. I explained that in the previous lecture. You can still get it in your notes. Here. Yeah, that is it. This is it. So when it's Fi plus 1, this becomes plus 1, this becomes plus 1, this becomes plus 1. And this is plus 1 minus 1 plus 1 is giving us 1. So that is what is happening. So plus 1, this will be plus 1, plus 1, plus 1. So this will be I plus 1, this will be I, and this will be I minus 1. And this will be I plus 1. That is what you are seeing for the corrector method. So we look at the truncation. So that is the first truncation. As you see here. When we truncate here, we get the AM1. And as you can see, we said Fi plus 1 is just f of the x and the y values. And this is the backward Euler, an implicit scheme. When we move on, we can truncate at the second term and simplify, and we are getting that. So the AM2 give us the trapezium method. The Adams-Moulton second order give us the trapezium method. We can move on to the next truncation. So that is what you are seeing. We simplify, and we have that. We have this. You can take time to expand, but that is what we are getting. We have this. We move on again. Usually we end at the fourth iteration, the fourth order, or the AM4. So when we truncate here, we simplify, and this is the fourth order Adams-Moulton's method. The fourth order Adams-Moulton method. This is a corrector method. I repeat, this is a corrector method. They are neither self-starting, neither can you start solving with this. You have to use a predictor method, and when the chosen predictor method is not self-starting, you might have to need a single step scheme to start this iteration. Similarly, there is a general form of the Miles-Simpson's method. the Marsh-Simpson's method. Also, depending on where you are truncating, when here we have the MS1, when we truncate here we have MS2, when we truncate here we have MS3, and when we truncate here we have MS4, here we have MS5. But note that this is 0, so our MS3 and our MS4 usually give us the same solution. Our MS3, MS4 usually gives us the same solution. The details of MS1 and MS2 have been exempted, but we have MS3, which is the same as MS4, because I'm adding the 0, that is why you are seeing MS4, but it will definitely give us the same solution as the MS3 case. So MS4, we have that, and when we do the appropriate substitution and simplify, this is our MS4. This is our MS4. So beautiful. This is our MS4. So this is also a corrector method. We are looking for I plus 1, and there's an I plus 1. So implicit scheme. When you come here, we are looking for I plus 1, and there's an I plus 1, another implicit scheme. But we just don't need I plus 1. We need at I minus 1, we need at I minus 2, making it implicit multi-step scheme. This is the same thing here. This is also implicit multi-step scheme. So let's look at how we can combine the predictor and the corrector methods we have talked about to give us just one scheme, what we call the predictor corrector methods, or what we call the PC schemes. So we have single step methods, or explicit single step method, Euler, modified Euler, Euler-Cauchy, Runge-Kutta. Explicit multi-step method, Adams-Bashford. These are all predictor methods. Then we have implicit single step method, backward Euler and trapezium. Implicit multi-step method, Adams-Moulton and Marsh-Simpson. These are corrector methods. Again, all the single step methods are self-starting. But the implicit single step method is also not self-starting. The explicit multi-step methods are also not self-starting. But why do we want to combine this? When you read whatever we have here, what we are saying is the explicit methods, the explicit schemes, they have weak stability properties, and the implicit schemes have strong stability properties. But when you want to use only the implicit scheme, you may have to do a series of iterations before you get to your solution. So what we do is we start with this and finish with this. We start with the explicit and finish with the implicit, so that we can get a more robust or a more fine-tuned solution. And that is what we have as the PC method. Here we are talking about the order. If the predictor method is of first order, the corrector method usually should be of first order, so that we can easily converge. The solution can easily converge. But if the predictor method, the order of the predictor method is, we are saying, is less than the order of the corrector method, then it might take some steps before the solution will converge. So we'll be using P for predictor and C for corrector. So watch here. So the predictor method, when we are saying we are using Euler, we are just giving some combination, some example. When you are saying you are using Euler, first order, then you can use backward Euler as a predictor, which is also first Euler. So you can predict this, which is implicit. Then you bring the value you find here, and you can use that as this is explicit, and you bring it here to form the implicit solution. You may have to also continue with several of these, where this C will be moving here like that as an iterative procedure to fine-tune your solution until the required accuracy criterion is satisfied. Another example, we can use the fourth order Adam-Bashford method as the predictor method, and we use the fourth order Adam-Moulton as the corrector method. So whatever we get here, we have to plug here. But this multi-step method will also require some single-step method to find to compute the values here. The values here should be computed using some single-step method, maybe given in the problem. So this will be a typical example for the corrector predictor method. So look at the example. We are saying we are using the fourth order Adams-Bashford Moulton, which means fourth order Adam-Bashford, fourth order Adam-Moulton, to evaluate y of 0.8 if this thing, the same question, but here epsilon is a very small number. Whenever you are seeing epsilon, then you know we may have to compare the solution, the current solution, to some previous solution to check the threshold. We understand how to get the values, the interval table values. 0, h, we add h, we add h, we add h. So that is the interval. We cannot go beyond the interval. That is the x interval. We have our y already, and then what we do is convert it to an iterative scheme. So straight away, the question is saying fourth order Adam-Bashford. That is a predictor method. So we write that. That is a formula. That is it. That is what you see here. So it is only when I is equal to 3 that we are going to have f0. When I is 4, it will begin with f1, and that is not the initial condition. Similarly, when I is same 1, this will be b minus 2, and we don't have f of minus 2 in our table here. It starts from f0. So when you look at this critically, so when you look at that, so it is only when we start from I equal to 3, then we will get not, we get 1, sorry, we're going to get 1, then we get 2 here, we get 3 here. So the first value we will be computing is y4, and that is superb. So when you look at that, the first value is giving us y at this point. So what happens to y3, y2, that? Where are we going to get the values from? And the question has stated that if you need them, use the Euler method. So you use the y values here to find that with Euler. You use this to find that with Euler. You use this to find that with Euler. Then you use this, that all together to find y4 for the predictor method. So that is what is happening here. We are starting straight with y4. I already know the solution for the Euler. I will not worry myself. You can visit the previous lecture and see, or you can compute them here again. But this is my Euler solution. So I need F0, F1, F2, F3, and that is what you see here. Papa, you see this, that, this over that, because of the given function. When the function change, please note, when the function changes, we have to change how we are computing this. These are functional values, and that is why you are seeing that this is over that. So this is F0, F1, F2, and F3. We plug them into the formula straight. We know Y3, this is Y3. We plug them in here and simplify. And that is the corrector solution at Y at 0.8. So that is Adam Bashford fourth order, the solution for Adam Bashford fourth order. That is the solution. That is the solution. If we were asked to find maybe Y of 1, we would have moved ahead to find Y5 of P. Then when we have gotten the solution, we will fine tune it with the corrector method. But since we have to find Y of 0.8, what we do is this solution, we have to fine tune this solution with the corrector method. And the question mentioned we have to fine tune this using the Adams-Moulton method. So that is Adams-Moulton's fourth order. But here, watch this, the yi plus 1, we have the p here and we have c here, meaning that the p is coming from the predictor method. And again, the value, we started with I equal to 3. When you watch here, where is it? I equal to 3. So we just the same thing here into the Adams-Moulton. I equal to 3. This will be 4. This will be 4. This is 3. This is 2. This is 1. Please, this method has been started with something. That is why we don't need F0. We pick the I value for the Adams-Bashford method. The I value we got the not the same I value, and it was 3, and we plug it in here. So you can see F1, F2, F3 like that. Note that we know F1, we know F2, we know F3. We know them. We will just pick those values and plug them here. But the new value is this one, the F4, where the Y value is coming from the Adams-Bashford method. The value here, but we know X4 to be 0.8. So we compute that the functional value, and we simplify to get the first iterative value. We are not stopping here. That is why you are seeing C plus 1. We may have to check the stopping criterion, and you have known in the previous lecture that usually we can't check the stopping criterion with the very first iteration. So we move on to the next iteration. That is still yi at 3. What is changing is this yp is no more that, but we are using this yc for that. So this y2 and this becomes y0. So this is c2 and this becomes c1. So we are picking the solution here and we are plugging it into the same function. Nothing has changed. The only thing that has changed is this solution. That is why we are saying corrector. We are fine-tuning the solution over time. So we plug it in here, we fine-tune, and we get that. So this is that. That is the corrector, the first iterative corrector. We had that. The second iterative corrector, we had the same thing, and it's so amazing. And we can say that this value is less than the given threshold, and we can stop the iteration. So we can say that y of 0.8 is 1.236. 1.236. This we found this using what we call the predictor corrector method, specifically the Adam Bashford Mothin's fourth order scheme, where we solve the previous solution. Because they are multi-step methods, we solve the previous values using the Euler method. So wonderful, so beautiful, so amazing. Oh, math is fun, math is beautiful, math is beautiful, math is. So these things are what we call numerical methods. We have successive approximation. We do that, we fine tune, we do that, we fine tune, we do that, we fine tune. So that is basically for the semester. We end it here, but this is also a final example for you to look at, a final exercise. We want to solve this using Ranjikuta. Using Ranjikuta, you are finding these values. Then you find the next value using the Marsh-Simpson. This is a corrector method. A corrector method. So you start this and you correct it using this method. It's the same thing. This is a different question where the y values have been given, so you don't have to worry your head. So this, instead of computing this with single step methods, they have been given here, and you use the appropriate multi-step methods to continue. That is the Adam Bashford. You first use the Adam Bashford of fourth order to find that, and you correct with it Adam Mothin of fourth order. It's been so beautiful. It's so beautiful. We will end the semester here. We will end the semester here. This so far. We started with what we call a basic introduction. We look at what numerical method was and some of the things that will be needing the semester: accuracy chopping, errors, and Taylor series and Maclaurin series, like that. We moved on to finding solutions to transcendental equations, the direct and the indirect methods or iterative methods. We look at system of equation, also the direct and the indirect method. We look at numerical differentiation, numerical integration. We move on to single step schemes for solving ODE, and we ended with multi-step schemes for solving ODE, with the predictor corrector method as the most final thing we did in the semester. There are some references for you. You can go through, and I believe it will be helpful. Thanks for being part of the semester. Thanks for being part of today's lecture. Stay blessed, and end of semester will basically cover everything. Till we meet again. Shalom.